In the second part, we have dielectric materials. That is okay. The first part, this Clausius Mossotti and local electric field. These two are very important. We will discuss that one. So first one. So what this equation means? It will explain about polarizable dipole moment, or you can say mu also. You can write relationship between dielectric dipole moment and polarizability. Okay, polarizability. It will explain relationship between dipole moment and polarizability. Suppose if you know polarizability, you can estimate the dipole moment of a dielectric material. Or if you know dipole moment, you can estimate the what is the polarizability. Okay, these two will explain relationship between dipole moment and polarizability, constant or polarizability. Okay, that's it. So now we know equation mu is equal to alpha into E, right? Alpha into E. Okay, this is the polarizable dipole moment equation, right? You know this equation. We have studied this one, right? Did you remember? Mu is called mu proportional to, or you can write, or how you get dipole moment is proportional to the electric field. Okay, dipole moment is proportional to the electric field. If you remove this proportionality constant, you will get the alpha E, alpha. Okay, this alpha is the polarizability constant. Alpha is the polarizability constant. Okay, now we are discussing electric field. When you dialect, when you keep the dielectric material in a electric field or parallel plate capacitor, we are estimating. So here you take a local field. Okay, local field. Okay, this is the equation one. It gives the just first we know dipole moment. Mu is dipole moment is proportional to the electric field. Okay, dipole moment means mu is called Q into D, right? Suppose if you give more electric field, here plus charge is there, here negative charge is there. Suppose after applying some electric field, suppose if you increase the electric field, more number of charges will induce on opposite phases. Okay, that's why we are saying mu is proportional to the electric field. Okay, our dipole moment is proportional to the electric field. If you increase the electric field, number of charges also induce. That means dipole moment also increase. Okay. So here we are taking local electric field. Okay. After that, so what we know is equal to yesterday we have discussed we have estimated the local electric field of total or Lorentz field. What is the answer? Yesterday we have discussed, right? Last in the last class. What is the answer? What is the final answer? Anybody please? What is the final answer? Did you remember? No, no idea. Anybody solved at least? No. I think you don't have time for this. Don't know? Okay, no problem. E plus capital P by E epsilon naught. Okay. Is this the correct one?
Yes, sir.
Yeah. Okay. You substitute this local electric field here. You just simply substitute here. Now, this is the local electric field of a dielectric atom when you keep within the parallel plate capacitor. Okay, within the parallel plate capacitor or within the external plates, external electric field, or you can say external electric field also, or plane capacitor also. Okay, here from there you simply substitute here mu is equal alpha into E local. We are substituting E plus P by 3 epsilon naught. E plus P by 3 epsilon naught. Okay. After that, we have one more equation, that is polarization. Okay. What is the formula of polarization? Polarization. Mu is the dipole moment. Okay. Or you can write small p also, but you will confuse polarization and dipole moment. That's why I am not writing small p. Okay. You proceed with mu. Okay. What is the polarization? Dipole moment for unit volume, right? Dipole moment for unit volume. Okay. If you take number of atoms, this you can write small n. Okay, this is the equation of polarization. Polarization means dipole moment per unit volume. Suppose if you consider n number of atoms, we are taking n. Here number of atoms. N means here number of atoms. Okay, number of atoms. So here mu means dipole means V means volume. Okay. So here you can rewrite this expression dipole moment mu is equal mu into capital N. Capital N. Here number of atoms or molecule, whatever you can take, it's not a problem. Okay. Here capital N is what here? What is the capital N here? This time rewriting this expression like this. What is the capital N now? This answer.
Number of atoms per volume.
Yeah, very good.
In
Okay. Yeah, good. Okay, number of atoms or molecules, whatever you can write, it's not a problem. Molecules per unit, per volume. Okay, we are taking like this. Okay, now what you will do, you have got the polarization and dipole moment. Okay, now our job is to, so here also what is the here again you see here mu is equal to, what is the equation again? Mu is equal, mu is equal alpha into E. Okay, alpha into E local, or you can here you, or you can sorry, already we have substituted here alpha is equal to this equation. Okay, this equation, and you simply take 1 2 3 4 like that, 1, and let's take this is 2, equation 2. Already we have substituted mu is equal to alpha e to e. In place of e we have written e local, then we have equation this one, and we have substituted equation 1. Okay, e local we have substituted in equation 1. So now you have written mu is equal to alpha into e plus p by 3 epsilon naught. Okay, in this equation p is equal to mu n, you simply substitute this equation. It's very easy, just only two formulas you have to substitute. Okay, now equation, let's take this is 3, substitute equation 2 in equation 3, equation 2 in equation 3. Now capital P is equal to mu means alpha e plus p by 3 epsilon naught into n. Okay, into n. This is the equation. So we will, after, what is the next step means, we have to rewrite this equation. We have to rewrite this equation. Okay, here what this polarizability constant is, we have electronic polarization and ionic polarization, ionic and dipolar polarization. Okay, what type of polarization we are discussing here? Electronic polarization. That means this constant is electronic polarizability constant. Okay, just you write alpha E. So you rewrite this equation. In the left hand side we have capital P, and right hand side we have capital P. We'll bring it two terms one side. Okay. Okay. Here we will multiply n alpha E E plus. This time multiplying alpha E and to these two terms. Okay, n alpha E capital P by 3 epsilon naught. Okay, now we will rewrite this expression again. This third expression, third term and first term, we will bring it one side. Okay, P minus, okay, n alpha E by n alpha P by 3 epsilon naught. Okay, n alpha E into E. Okay, can we write like this?
yes, sir.
Yeah, we can take out this P outside. Now we'll get 1 minus n alpha E by 3 epsilon naught. Okay. Now here n alpha E. Okay. This is we got. Next we'll simplify. We'll send this term also to right hand side. Okay. P capital P is equal n alpha E by, here 1 minus n alpha E by 3 epsilon naught. Okay, this is equation. Let's take a 4. Now, how to approach next step means, okay, we know D is equal epsilon naught E plus P, right? We know this equation. Displacement vector is equal to P epsilon E plus P. Okay, from there you can write P is equal. You can write. Can you write P is equal? Capital P is equal. You can write this way. D minus epsilon naught E. Okay, D minus epsilon naught E. Okay, after that, what you will do? So simply you divide with E both sides. Simply divide with both sides E. Okay. So we are dividing both sides capital E. Okay, electric field we are dividing. Okay, after that, okay, you rewrite again this one. P by E is equal D by E minus this E cancel out and we will have only epsilon r. Okay, from there, here what we can write, D is equal epsilon E. Can we write like this? Displacement vector is equal to the medium permittivity and electric field. Okay, this expression we know. Okay, simply D by E means here what we can write? D by E is equal to what we can write? Epsilon, right? So you simply substitute that expression. Epsilon minus epsilon naught. Okay, here P by E. Okay, here P by E. From this expression, we can write this P is equal. You send this E outside this side, right hand side. E epsilon. Sorry, this is epsilon. Okay, whenever you are writing this problem, okay, E is you write is like this. Okay, some people
Your
what they
voice
will
is
do,
breaking.
they will write E also like this. Okay, this is not right way. So E means electric field, and epsilon means voice is breaking. Just a second. Is it clear now? Can you hear? So whenever you solve this problem, whenever you are writing exam, E means you write like this, okay, capital E. This is electric field. Okay, this epsilon is permittivity of medium permittivity. Okay, careful with these two terms. Okay, so here we are writing E into epsilon minus epsilon naught R. Okay, what is the dielectric constant or relative dielectric constant is equal to? What is the value here? Epsilon R is equal to our relative dielectric constant or dielectric constant. Okay, what is this? How you will define this one? Tell me. Relative dielectric constant or dielectric constant. How you will define? So daily class you go through at least 5 minutes. Then it is easy. Okay. Medium permittivity to free space permittivity. Relative dielectric constant means medium permittivity to free space permittivity. This is what dielectric constant means. Okay, from this expression we want only epsilon, right? Epsilon we want, so you can write epsilon r minus into epsilon naught. Okay, can we write like this, right? So from this expression we are writing P is equal to E into epsilon r epsilon naught minus epsilon naught. Okay, this is from this expression here in the two terms we have epsilon naught. So we will take out this epsilon naught outside. Okay, E into epsilon naught minus epsilon r minus 1. Epsilon r minus 1. Here P is equal to capital P is equal to. Okay, this is, let's take equation 5. Much, yeah, let's take 5. So now you substitute 5 in 4, equation 4. So what is the equation 4? Capital P is equal to n alpha E by 1 minus n alpha E by 3 epsilon naught. Okay, okay, here you substitute P is equal to this one. E is equal E epsilon naught epsilon r minus 1 is equal n alpha e by what is the equation? 1 minus n alpha
N
e by 3 epsilon naught. Okay, very good. Thank you. So here you have to slightly means you rewrite this expression. You have to rewrite this expression. Now here no need to uh, worry for here. Just we have to rewrite this expression. How we will rewrite? I will tell you. So what you will do here? Here this E and E will be cancelled out. E and E will be cancelled out. So here this term, here you carefully observe this one. So we want relation between mu and mu and mu and epsilon alpha e sorry alpha e we need. Okay, this one we need. Okay, so for that according to that equation we have to rewrite that expression. Okay, we have to rewrite according to that. Okay, so here so I am bringing this term left hand side. Okay, 1 minus n alpha e by 3 epsilon naught, and here we are, I am bringing n alpha e by here epsilon naught into epsilon r minus 1, epsilon r minus 1. Okay, now I, I rewrite like this expression. So this term what I done, okay, this term I bring it to left hand side and this term I bring it to right hand side. Okay, so after that we will bring this what will bring it only you keep one left hand side and remaining bring it right hand side. Okay, or you can say this one slightly you have to read at this one. Okay, here see in the right hand side we have n alpha e by epsilon naught. Okay, n alpha e by epsilon naught. In the left hand side also we have n alpha by epsilon naught. These two we have same. Okay, we will bring it one side. So 1 is equal n alpha e by 3 epsilon naught plus n alpha e by epsilon naught into epsilon r minus 1. Okay. From there what we can take out common? N alpha e by epsilon naught can we take out? Can we
Yes, sir.
yeah, we can take n alpha e by epsilon naught you can take out, or 3 epsilon naught also you can take out here. You can take 3 also you can take it, or you can without taking 3 also you can do it. 1 place here if you take like this 1, so what you will have in the numerator?
3.
Yeah, 3. Okay, next in the denominator we have epsilon r minus 1, epsilon r minus 1. So because already we have epsilon n alpha e we taken out, so this term only will remains here. Okay, we will again we will simply rewrite or simplify this expression. Okay, epsilon r minus 1 plus 3 by epsilon r minus 1. Okay, so after this one what we will get? N alpha e by 3 epsilon naught, here epsilon r minus 2 sorry r plus 2 by epsilon r minus 1. Okay, this is 1. Okay, now our job is done. Okay, you send this term right hand side. Okay, sorry left hand side, epsilon r minus 1 to epsilon r plus 2 is equal to n alpha e by 3 epsilon naught. Okay, this is our final expression. Okay, final expression, it explains, it gives the relationship between epsilon r, that is dielectric constant. Okay, what is this one? Dielectric constant, and this alpha is the electronic polarizability constant. Polarizability. Okay, electronic polarizability constant or electronic polarizability. Okay, so this gives the main relationship between dielectric constant versus polarizability. Okay, here capital N is what? Capital N is what?
Number of atoms or molecules per volume.
Yeah, number of molecules per atom, molecule per volume. Suppose you know 10 molecules and is called 10, and you know epsilon permittivity 8.85 into 8.10 power 12 farad per meter. Okay, this you know, and suppose if you know electronic polarizability, you can estimate the dielectric constant of a material. You can estimate the dielectric constant of a material, or if you know dielectric constant, you can estimate the electronic polarizability. Okay, this is alpha E. This you can estimate. So this, suppose you are saying it is a good dielectric or bad dielectric, main parameter is the dielectric constant. If you know dielectric constant, you can you can study the which type of dielectric material. That means we can say it is good dielectric or bad dielectric, and according to that dielectric constant we can use in different applications. Okay, now see some examples of dielectric materials. So this what will take, teacups, pingani teacups are there, no, this also dielectric. And also in many this materials, suppose military applications, defense applications also will use the dielectric materials. And also oven, you know, right? Microwave oven, do you know, right? Microwave oven,
Yes, sir.
microwave oven. Okay. So generally in our homes also we'll see, when you go this canteen or something like that, whenever we reach there, they will immediately they will heat our item and they will give, right? So this is also we'll use the dielectric materials and we can prepare. Depends on dielectric constant. Okay, depends on dielectric constant. We can see the properties of dielectric material. Depends on properties. We can apply different applications. We can use in different applications. Okay. So this suppose you have studied LED, you have studied, right? LED or PN junction diode or solar cell. This you have studied. So how you will define the good, so good device? It is a good device. How you will study this one? Suppose LED is good device or solar cell is good device. It is giving best properties. How you defined? How you identified? By studying IV characteristics, right? By studying IV characteristics. By understanding the IV characteristic, we can identify which one is good diode, which one is good bad diode. Okay, here also, like that, dielectric constant also very very important property of a dielectric material. Okay, so here polarizability, if you apply electric field, how the polarization is taking place, how easily polarization taking place, this polarizability constant will explain. Okay, now, so this is the very important. I explained very step by step. That's why you feel very lengthy, but it is very easy.